This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
So welcome back to the next tutorial on cosmology of the WE-Heraeus International Winter School on Gravity and Light. And again we have some statements. Today these are 10, and it's, as I said, about cosmology. And an important notion for cosmology is what a maximally symmetric space is. And by maximally symmetric we mean that we have the maximal amount of Killing vector fields. And the first statement on that is homogeneous and isotropic 3 manifolds are maximally symmetric manifolds. That is right, since homogeneous produces 3 Killing vector fields and isotropy produces also 2, so translations and rotations. These are 6 in total, and if you look at the formula, that is d times d plus 1 over 2. Basically that's the number of independent components in the metric. And if you plug in the 3 here, that's 3 times 4 over 2 is 6 in our case. And these are precisely these 6 Killing vector fields. So that's right. Therefore, these are maximally symmetric. A 5-dimensional manifold can have maximally 10 linearly independent Killing vector fields. By the same formula this is incorrect, because 5 times 6 is 30 over 2 is 15, not 10. Riemann curvature on a maximally symmetric manifold contains exactly one derivative of the metric. No, it doesn't. We saw that it contains no derivative of the metric. A maximally symmetric 3 manifold cannot be flat. Yes, it can. For example, consider the spatial part of FRW. If we pick kappa equals 0, then we have this maximally symmetric 3 manifold that is flat. So this is false as well. And the last one for part A would be a maximally symmetric space has constant sectional curvature. These are the kappas, so minus 1, 0 and 1 that we introduced in the lecture, so that's true. B. Which statements are correct? Perfect fluid matter has constant pressure and constant density over the whole space-time. Definitely not, because the P, which is the pressure, is some function of T and the rho as well. So that's incorrect. Homogeneous and isotropic dust and radiation can be modeled as a perfect fluid. That's right. So we saw that the equation of state, that is this one, for omega equals 1 over 3, we model radiation, and for omega equals 0 we have dust. So that can be modeled, and this equation of state is the equation of a perfect fluid. That's how we call that. The Friedmann equations are the Einstein equations for a spherically symmetric vacuum. So up to here this would be correct, but it is not a vacuum. It is not necessarily spherically symmetric. In particular, it can just be spherically symmetric in the spatial part. So this is definitely not correct. But the main argument is here vacuum, because we put matter on the right side. The FRW metric with kappa equals 1 is the metric of a hyperbolic 3 manifold. If you put a minus here, this would be correct, but since there's no minus, this is incorrect. Remember this factor 1 over 1 minus kappa r squared, and kappa equals 1 produces a spherical 3 manifold. The last one, all matter densities rho of t are proportional to t to the minus 2. That's right, and we calculated that in the lectures. Exercise 2, Killing's equation. first, before we start deriving Killing's equation, we want to again think about what it means for a vector field K to be a Killing vector field. And we should give some interpretation of this condition in terms of the flow HK associated with that Killing vector field. So the condition for the vector field K to be a Killing vector field was that the Lie derivative on the metric with respect to this vector field vanishes. Okay, so we should give the interpretation in terms of the flow. Where does the flow come into the game? Well, LKG was defined as HK, some parameter y lambda, the pullback of the metric minus G over lambda, and as always I forgot, we need to take lambda to 0, so some limit lambda goes to 0 over that. So this is some more general form of a differential quotient that defines the Lie derivative. Okay, but in order to do the interpretation here, we first need to say what this flow HK is really about. So in order to understand that, we look what it does. So we look at this map, which takes some value r, the lambda down here, and some point, and maps this in the manifold again. So it gets the tuple lambda p, and this is mapped to HK of this tuple. So just plugged in, and normally, because this looks a little bit silly, we write h up k down lambda, so this parameter lambda jumps here of p, and this one is just gamma p of lambda. But now you have to ask what is lambda, what is gamma, and I need to tell you that, and that is the tangent vector to the curve gamma at the point P. Has to be the Killing vector field at the point P, that is the vector at this point. If we have this condition, then we call HK the flow of the vector field K. Okay, so we maybe draw some picture. And to use again the terminology introduced, these gamma here are the integral curves through the vector field, and if we do that for all of the points, then we call the parameter subgroup of integral curves, this we call the flow. So this here would be the HK lambda, and the lambda varies in this direction, and the point P that we plug in here sets somehow the starting point, and if you plug in Q and Q is down here, then we arrive at this integral curve. So this would then be gamma Q of lambda, this up here would be gamma P of lambda. That's the idea of the flow, and as we know, we can use such maps to pull back tensorial objects, for example the metric. So we look at the metric here, for example, and look at the metric here, but in order to compare them, we pull them back here and we look at the difference of these two. And the meaning of the Killing condition here is that they don't differ. So the metric here and here is the same, and that's how it is mathematically encoded. Okay, next question. Show that a vector field K is Killing if and only if nabla AK down B plus nabla BK down A equals 0. And this one is called Killing's equation. Okay, so you may have seen this before, but now we want to do the derivation of this result. Okay, so the only thing that we know is that K is a Killing vector field. So the only thing that we can write down is Lk on G, we look at this in coordinates, equals 0. And now we try to write some equal signs in order to arrive at some expression that looks like that. Okay, so the Lie derivative on a 0-2 tensor consists of 3 components, so Kc d by dxc acting on GAB. Now we have the indices down, therefore a plus, and now we introduce the summation index down here, and the derivative d by dx A acts on Kc, so the sum is here. Now we do the same for the other index, so this is G, oh sorry, here's something going wrong, this should be a B, just replace the A by the C and shift the A over here, that's the rule. And now we leave the A and put the C here, and then we get d by dx B, because the B from here moves there, and this acts on, not on X, but on K. And the index that needs to be summed over is C. So that's basically it. So the Lie derivative in components. Okay, so the next thing to do is we somehow need to produce gamma symbols. Why? Because here is the covariant derivative, and if we write this in coordinates completely, we get some gammas. And therefore we probably need to recall the definition of the gammas, and I put this up here. So some gamma A, B, C is defined as 1/2 G, A, D, and in here we have the metric G, B, D, comma, C. I again use the short notation here. G, A, D, comma, B, plus, oh that's not right, the A can't be down here. So what is it? We have B, C, and now we have C, D, comma, B, that's good. And here is no plus but a minus, G, and now we have B, C, comma, D. That's the definition of the gammas. Sorry for the small space here, but you should know that by heart. Okay, so we see that here, for example, this would be GAB, comma, C. That looks similar to this one. And we should try to produce these two terms here. So what we could do, have a closer look at this one and pull the metric in here. This produces some mistake that we make, and this needs to be compensated. So this looks like G, A, B, comma, C plus. And now I make the mistake by writing d by dxa on G, C, B, K, C. So here I would have to evaluate this by the product rule, but here only one of the two summands appears. That means we need to subtract the other one, and the other one is just the Kc untouched, and here we have G, C, B, comma, A. So this here is the same as this expression, just inverse application of the product rule. Here we do the same. That means we have d by dxb on G, A, C, K, C. And to compensate this mistake that we make, we write Kc, and here it is GAC, comma, B. Okay. And now we do a little reordering and write this a little bit shorter. So GCBKC is nothing but K, down B. So this would be K, B, comma A, because we derive by A. Same holds for this term. That means we have a plus K, and now it is down A, comma B. And this looks quite good, but we need to make the partial derivative here into a covariant derivative, but fortunately we have the gammas that we first need to find, but I assure you that they are there. So we write this as the Kc that appears here and here and here pulls out, so we can put this in front, and what's left is GAB, C minus GCB, A minus GAC, B. Okay, and now we need to have a closer look at this one. So we just keep these two and do this step by step. Plus, so K up C can also be written as K down, let's say, D. We have no D in there, but G DC. Okay, so these together just would pull the index up, and in here we have, what I want to do is put the minus here, so this one goes out, and therefore we have GCB, A plus GAC, B, these two, but with the opposite sign, and here it is, this is GAB, C. Okay, that's it. And now we know that the metric is symmetric in these indices, and what that means is we just have twice the gamma here. So this is KD, and now we have twice the gamma, because if you remember, here was some factor 1/2, and here we put the 2, and that is now, let me see, the C is summed over, so what we have here is a D up and some A B down. So we sum over the D and AB remains, and the index structure fits. And now we can do some reordering. So we know that this is symmetric in these indices, so we can distribute the two gammas onto these two. Here we missed some comma, I'm sorry. And that means we have K A, B minus, and now it is gamma D A B K D plus K B, A, this one, minus the other gamma, that's KD BA KD. Okay, but this can be short written as nabla A acting on K, the bth component, plus this plus here, nabla what is it, B K, the eighth component. Okay, and if we compare up here, that's the same. So we arrived at the right result, and since we just started from LK on G, which is 0, we derived the Killing's equation. Okay, that's it for this exercise. We continue with exercise 3. In exercise 3, we want to estimate the age of the universe by some specific matter model, and we start by first deriving the conservation equation that we need in order to manipulate the Friedmann equations such that we can get the desired result. So the exercise is: the energy momentum tensor for a perfect fluid is given by this expression that you might know from the lectures or somewhere else, and this UA is some time-like vector. or the components of some time-like vector. Okay, we want to choose these coordinates, and the condition that we use is basically the energy conservation, or the energy momentum conservation that followed from the differential Bianchi identity that we showed last time, that is, or the twice contracted differential Bianchi identity, that is that we have nabla A on G, a bth component, this is 0. And if this holds and the Einstein equations hold, then this holds without the UB here, but adding the UB will change nothing. But this will just make it a little easier for us to derive this. Okay, so we start by evaluating this condition. So nabla A on T, a bth component times UB, but this is just nabla A T A 0. Maybe some minus in here, but this doesn't interest us because the other side is 0 and this would cancel. So that's the expression where we start, and we just write this. So nabla A T A 0 is, okay, so we have T A 0 comma A. Now indices are up, therefore plus. Now we have gamma, here's some T, and for the other index as well, gamma and the T. Now we need to distribute the indices. So we derive by A, therefore the A goes in both cases here. Here goes some dummy summation index, and here we put the A up here, and then the N goes there. And then we are missing something, that is the 0 here, that stays untouched. And here it's the other way around, the 0 goes here, and the A stays, and the N goes there. That should be right. Okay, so in order to calculate this, we need the gammas. And I will give them to you. So this is gamma A NA is equal to gamma alpha N alpha, where the A's run over 0, 1, 2 and 3, and the alphas just 1, 2, 3. This holds, as we showed in the lecture, and this gamma symbol is given by A dot over A, and here's some delta alpha alpha. But we know what that is. We contract here, and this yields the dimension. In this case, for the spatial indices, A3. So we know what this guy is. Is that right? Ah, okay, I was too fast here. I wanted to put some 0 here. So this is now correct, and we'll see in a minute why we need that. Maybe you do this now. Okay, so we know that the 0th component, if we have the row 0, the column 0, then this has to be a 0 too, because otherwise there are no contributing entries in the energy momentum tensor. Therefore this is row dot, and by dot we denote the derivative. So this one has to become a 0, and of course this one as well. So we derive the first component, that is just rho, because the p here cancels, and then derived by t. And we denote this as rho dot. Now comes a plus, and now we argue here the same way. This has to be a 0, therefore this has to be a 0. And now we can use the gamma that I wrote down here, maybe a little bit fast, but nevertheless that's true. So what we have here is 3 times a dot over a. We use this. And t00 is again just rho. Okay, now it gets a little more complicated, but nevertheless we will do that. And we write this as gamma 0, and now we put Greek indices here, alpha, beta, over which we sum. This is symmetric, therefore the order doesn't matter. And we know that in the gamma there's some 0 anywhere, then only the spatial part contributes. That means we can rewrite this as just a summation over the Greek indices, which are the spatial ones. And now we can have a look at this guy. And this was given in the lecture as well. And this is A times A dot times gamma alpha beta, where gamma alpha beta down was G alpha beta, what do I want to say? So G alpha beta was A squared times gamma alpha beta. So this was just the spatial part, and in the whole metric we want to multiply that by the factor A squared. Good. So we know what this one here is. So this is plus A times A dot, and we have some gamma alpha beta here. And now we have to look at the spatial part of the energy momentum tensor. That is just P times GAB, but G up AB, and just the spatial part, so alpha beta is 1 over A squared gamma alpha beta. Okay, so here goes some 1 over A squared gamma alpha beta, and here's the sum. And again, this whole contraction here produces the dimension that is again some 3. So we have rho dot, and now we evaluate. This 2 cancels against this one, so we have A dot over A, the same as here. This one pulls out. These two yield the dimension. Therefore this is 3 A dot over A rho plus P. I forgot the P. This P, where is it? This P, I forgot. So that's it, and this should be 0. And if you have a look, this is the desired result. Okay. So, to summarize, we exploited the condition that the covariant derivative of the energy momentum tensor in one of these directions yields 0, which follows from the twice contracted differential Bianchi identity that we derived last time. And then you have to play around with the indices here and look at the non-vanishing components here. And then if you do this carefully, you arrive at the right result, as I hope. Yes, so that's good. And I suppress the of t over here because that is not that important here. Okay, so in the next question, for p equals omega times rho, that means we have a perfect fluid, we should solve this equation above for rho, and then use the Friedmann equations with vanishing spatial curvature. That means here is no contributing term to derive an autonomous differential equation for the A. So we want basically to eliminate this rho and replace by something with A or A dot or whatever. Okay, so the first step, as it is given in the question, we should have a closer look at this expression, and we better write this in the given form. So this is minus 3 A dot over A rho plus P. Yes, that's right. And this is of course the same as rho dot equals minus 3 A dot over A, and now we know the equation of state here. That means we can pull out the rho, and here it is 1 plus omega. Good. Now we divide by rho, that means rho dot over rho equals 3 times A dot over A plus omega. And this is the same as d by dt, the natural logarithm of rho, and here the same thing, d by dt logarithm of A times 1 plus omega. Now we continue up here. So we integrate this once, so we get log rho equals minus 3 log ln A times 1 plus omega. Now we take this, some exp of that, so we get rho equals, and we know what happens with factors in front of the logarithm, they just go up here. That means what we have is A to the, what is that, minus 3 times 1 plus omega, and we suppress the constant, or we could introduce it as well. So here plus c, and then this is some c tilde in front of here. That's right. So that's the expression for the rho, and we should plug this in to that equation, so star into 1. So we get A dot over A squared equals 8 pi g over 3 times this constant times A to the minus 3 times 1 plus omega. And that's our result, because we wanted some autonomous differential equation for the a's. So here we just have a's in there, the rest are constants. So that's the result. Now in the next question, the differential equation should be solved. And I write it down again. So this was A dot over A squared, and that was equal to 8 pi g over 3 times our constant c tilde, that we may suppress as well, but doesn't matter. And here we have A to the minus 3 times 1 plus omega. That was the differential equation, and the ansatz here is given, so we just plug this in here. And what I will do is just collect all the constants that appear here and pull them into some new constant d. And what we have here is A dot, that means derivative with respect to the time. So here we have t alpha minus 1. The alpha here again went into the d. And down here we have t to the alpha, that is squared, and here all these factors went in there as well. So what we have is a, nope, not a, but t to the minus 3 times alpha times 1 plus omega. Okay, now we do some reordering. That means we have d equals, here the alpha somehow cancels and we get t to the minus 2, and put this to the other side, and that means we get some plus 2 here. Okay, and since here's some invisible t to the 0, in order for this equation to hold, we need to say that minus 3 alpha times 1 plus omega plus 2 equals 0. Otherwise this equal sign cannot hold. And from that we can read off the alpha. We bring this to the other side, divide by 3 and by this. So this is 2 over 3 times 1 plus omega. Okay. And what I forgot to mention is that we just consider omegas not equal to minus 1, because then this would vanish and then this would not be a solution of that one. So we found the alpha and therefore can write down the a of t, which is then the constant c times t to the 2 over 3 times 1 plus omega. And by the way, we want the c to be greater than 0. We will need this later, and this makes sense because the scale factor should not decrease in our model here. Okay, we continue with the next question, where we actually arrive at the age of the universe, and the question is the following. So we should use this result of the previous question to write down an equation for h of t, which is the Hubble function defined by a dot over a, and then estimate the age of the universe only filled with dust for today's value of the Hubble constant, given by that. And afterwards we should do the same thing, not for dust but for radiation. So we do this first in general. Look at this function. So h of t was defined by a dot over a, and if you look at our a, this is just some, well, I write it down. So this is, the c cancels of course, and we get t to the 2, 3 times 1 plus omega, minus 1 because we derive one time, and then we have this thing times, well, this one comes down, 2 times 1 plus omega, divided by just t to the 2 over 3 times 1 plus omega. Okay, now we cancel everything that can be cancelled. Here's 1 plus, so this one goes against this one. So what's left is 2 over 3 times 1 plus omega times 1 over t. That's all that's left. Okay, and now we look at first the dust model. That means omega equals 0, equivalent to 0 pressure. So that means we have H0 equals, now we plug that in here, so that yields 2 over 3 T0. Now we can solve that one for T0, which is 2 over 3 H0, and now plug in the given Hubble constant for today or last week or something like that. So we use that, and the result would be 2/3 times 13 times 10 to the 9 years. Well, that estimates the age of the universe as some value if we assume that everything is just filled with dust. The same goes for radiation. So we have omega equals 1 over 3, and then we can just write out what this is. So omega equals 1 over 3. That means we get some 1/2 here, and we have this one. And now this gets 6.5 10 to the 9 years. So you see, for different models that we impose, we get different results for the age of the universe, for some estimate of that. Of course, this whole thing is much more complicated, but I think it's quite nice to have such an easy model and get such good results. Okay, so that's it so far. And the last question is not about the age of the universe, but whether the expansion is accelerating or not. And this will again depend on the omega. And in order to talk about the the rate of the expansion, we need to look at a double dot, which is then 2 over 3 times 1 plus omega. That was the factor from the first derivative, and now we get another factor, which is this one minus 1, and in the exponent we have t to the, what is that, 2 over 3 times 1 plus omega minus 2 now. So that can easily be derived. I missed the factor c, and here you see why I wanted this to be greater than 0, because otherwise I would have trouble to say whether this complete factor here in front is greater or smaller than 0, because that's the statement on acceleration or deceleration. Okay, so we want to maybe made in total. So this is greater than 0. This is of course also greater than 0 because t is greater than 0, and therefore we look at roots of this factor, and this can only be 0 if 2 over 3 times 1 plus omega equals 1. That should be right. Let's continue and then we will check if this is right, but I think so. So that means we have multiplied that over here, so 1 plus omega is equal to 2/3. This over here, the 3 stays, that's good, and this means omega equals minus 1/3. So this is the point where we have 0 acceleration of the expansion, and now we can say that if omega is larger than 1 over 3 and if omega is larger than minus 1 over 3, we can make statements about the a dot dot. So that means larger than minus 1/3, we could for instance plug in 0. If we plug in 0 here, what do we get? We get 2 over 3 times 2 over 3 minus 1. That means this one gets negative, this is positive, therefore here the acceleration is not an acceleration, so the expansion is decelerating, and here we have it the other way around. So you see, for different matter models we get different statements on the expansion of the universe, namely whether it's accelerating or decelerating. And as you see, we have measured that the expansion is accelerating. That's one of the results of present measurements, and that means the omega in this simple model must be negative. But we cannot associate normal matter to that. So this would maybe be some indicator for dark matter or dark energy. But of course only in this very, very simple model that we choose. Okay, so this completes this tutorial. See you next time. Thanks.